So the next set of chapters involves stoichiometry and chemical reactions in chapter 4. And then in chapter 5, we're dealing with solids, liquids, and gases and looking at the different properties of those. And so when we're dealing with chemical reactions, chemical equations, one quantity that we have to talk about is the mole. And the mole is not the mole that you find in the ground, it's actually a number. And so the mole helps us determine the number of entities in a given mass. And so whether or not you have 26.98 grams of aluminum or 137.3 grams of barium, they're going to have the same number of atoms in that mass. And so these masses that I just read off, they're actually located on the periodic table below the element symbol. So if you look right now at a periodic table, depending on which one, it'll be close. They may round, but for aluminum, you'll see it's 26.98. For barium, it's 137.3. And so within that mass of aluminum and barium, they have the same number of atoms. And whether we're talking about masses or atomic masses, it has the same ratio as well. And so the number of atoms that are present in 26.98 grams of aluminum or 137.3 grams of barium is called a mole. And so a mole is the SI unit for amount. So anytime we talk about amounts, we're talking about moles. And moles, as you'll see later on, is how we're going to get between, in chemical reactions, how to get from reactants and products. In masses, how we go from masses of something to the number of atoms. It's all through the moles. So the mole is a very important quantity. And the mole is officially, one mole is officially the number of carbon atoms in 12.01 grams of carbon. And that's because carbon-12 is very stable. That's why we base it off of the number of carbon atoms in 12.01 grams of carbon. And that number is 6.022 times 10 to the 23rd. And this is referred to as Avogadro's number. And so generally on October 23rd, we refer to it as Mole Day. And so Mole Day is October 23rd. And if you're around the university, which we're not, but you would see they would be selling, sometimes they sell little mole keychains and whatnot on that day. So a mole of anything is 6.022 times 10 to the 23rd of that quantity. So if you had a mole of electrons, it's 6.022 times 10 to the 23rd electrons. If you had a mole of atoms, it's 6.022 times 10 to the 23rd atoms. If you had a mole of hair, it's 6.022 times 10 to the 23rd strands of hair. So regardless of what you have, if it's one mole, it's going to be that many of that entity. I like to call it entity. So whatever entity you're working on, one mole of that is 6.022 times 10 to the 23rd of that entity. And so, for example, just to give you a little prequel, if we're dealing with covalent compounds, those are compounds with nonmetals. Their entities are molecules. So they're made up of molecules. So one mole of, for example, methane has 6.022 times 10 to the 23rd molecules of methane. So if you have a covalent compound, the entity is molecules. So one mole of methane, 6.022 times 10 to the 23rd molecules of methane. Again, covalent compounds only have nonmetals in the formula. Now, if we're dealing with ionic compounds, they're made up of course, ions, but the actual entity that makes up ionic compound is a formula unit. It's similar to a molecule is for covalent compound. It's a formula unit is like a, you can think of it as a molecule. It's not really a molecule, but you can think of it as a molecule for ionic compounds. And so if we had 1 mole of NaCl, we would have 6.022 times 10 to the 23rd formula units of sodium chloride. And so these are what we mean by entities. And so the most common ones are atoms, molecules, formula units. So atoms, of course, are made up the entities of elements. So if you have 1 mole of silver, it has 6.022 times 10 to the 23rd atoms of silver. Now for compounds and elements, we have what's called the molar mass. So that's the mass of 1 mole of substance. And again, for the actual elements, if you look on the periodic table, if you have one handy, you can take a look at it. The number below the element is the molar mass of that element. So if you were to look at the hydrogen, which is the first element on the periodic table, typically it's reported as 1.008 grams per mole. Or if you look at oxygen, it's 15.999 grams in 1 mole. So that's where we get the molar masses of the elements. They come from the periodic table. Now for substances that are not elements, say compounds, what we need to do is we add up the number of each type of element in the compound, multiply it by its molar mass, and then we add up each element's contribution to the compound. And we'll look at some examples of that in just a second. Some alternate naming for molar mass for ionic compounds, we use what are called formula weight. So if you hear the term formula weight, it's the same thing as molar mass, except because ionic compounds are made up of formula units, they refer to the weight as formula weight. It's calculated the same way. It means it's the same number, nothing different. For molecular compounds, sometimes we use an alternate name called molecular weight. Again, it's the same calculation, the same process, just a different terminology depending on where you're reading. So I'm going to show you how we calculate molar masses of compounds. And this is important because if we have the mass of something and we want to know, for example, how many atoms we have of that substance, we have to go through moles, and the way we do that is the molar mass. So molar mass is like a conversion factor between grams and moles. So for methane, which we mentioned earlier, it has 1 carbon and 4 hydrogen. So if you go to the periodic table and you look up the molar mass of carbon, you'll see it says 12.01. So 1 times 12.01 gives us 12.01. Next, we have 4 hydrogens, which we can signify as 4 moles of hydrogen. If each mole weighs 1.008, we have to multiply by 4 to get the contribution from hydrogen. Then when we add these two together, we get the molar mass of methane. So again, the molar mass, you can think of it as a conversion factor. So 16.04 grams of methane equals 1 mole of methane. And so if we have the mass of something and we want to find the moles, or excuse me, we have the mass of methane and wanted to find the moles of methane, we would use this conversion factor here. If we look at ammonia, NH3, NH3 has 1 nitrogen, and if you go to the periodic table, you look under nitrogen, you'll see it has a molar mass of 14.01. So we multiply it by 1, we get the contribution of nitrogen. Next, we have 3 hydrogens. Hydrogen has a molar mass of 1.008. So we get the total contribution of the molar mass from hydrogen, and then we add it together. and we get 17.03. So again, this is like a conversion factor between mass and moles. So if you have a certain mass of ammonia and you want to find the moles, you would use the molar mass. And sometimes people like to use a little pictogram to know how to convert between the three quantities, mass or two quantities, mass and moles. So we have this triangle here. And so we have the molar mass in this section. We have the mass. Let me undo that. We have the mass here. And we have the moles. And so if we want to find the moles, we take the mass divided by the molar mass, which is what we just calculated here. If we want to find the mass, we take the moles times the molar mass. So you see, this is how molar mass links the two quantities, mass and moles. So if we take the mass and divide by the molar mass, we get moles. If we take the moles and multiply by the molar mass, we get mass. This is how we interconvert between these two quantities. So let's look at a few more examples of calculating molar mass. So again, this triangle is very important. And make sure you make a note of this. So mass over molar mass gives us moles. Moles times molar mass gives us mass. These two calculations will be done a lot when we're dealing with stoichiometry. So here we want to know how many so the mass is on top. So little m is mass, so that's on top. Molar mass is on the bottom. Now, if we're talking about the periodic table, the atomic mass is the same thing as the molar mass of that element. But when we're talking about compounds, the molar mass is calculated from the contributions of each, contribution of each component in the compound. So here I've written this triangle again. And so we want to know how many moles are contained in 315 grams of sodium sulfate. So we have 315 grams of sodium sulfate. So we know the mass of sodium sulfate is 315 grams, and we want to calculate the moles. So moles we don't know, mass we do know. So to calculate the moles, we need to take the mass divided by the molar mass. Well, you see, molar mass has not been given to us in the problem. And so what we need to do first is calculate the molar mass of sodium sulfate. And so the molar mass of sodium sulfate, and for sodium, we have two sodiums. And if we look at the periodic table, again, it's the number below sodium, the decimal number typically. It's 22.99. So there's two sodiums. Each sodium is 22.99. Then we got one sulfur. Sulfur is 32.06. And then we have 4 oxygen. Oxygen is 15.999. So again, we're going to multiply each element by its molar mass, or the number of each element by its molar mass, and then add them together to get the molar mass of sodium sulfate. And we get 142.58. And this unit is grams per mole. So again, we can write this as a quality conversion factor. So 142.58 grams equals 1 mole of sodium sulfate. So now we have the molar mass, we have the mass, we can draw a train track. And we can get the moles of our substance. Now take a note that 1 mole weighs 142.58 grams. If we have 315 grams, that's greater than 142. So our number of moles should be greater than 1. So we have 315 grams sodium sulfate. So since we're starting with grams, and also from our triangle, we know that we should divide mass by the molar mass. So we're going to put the molar mass on the bottom. And we're going to put the mole on top. So now we just divide and we get the moles of sodium sulfate. So we get about 2.21 moles of Na2SO4. Now with chapter 3 or stoichiometry, as long as you put 3 or 4 significant figures in the answers, that will suffice for me. I'm not a big stickler on significant figures once we leave the measurements chapter. So just one small error. I had incorrectly added the molar masses. So the molar mass of sodium sulfate is 42.036, and it slightly changes the answer to 2.22. So on that note, we'll go to the next one. So here we have a different approach to the problem. It says, what is the mass of 4.87 times 10 to the negative 3 moles of cobalt-3 nitrate? And the reason I chose this problem, is because we're going now from moles to mass, and B, we're going to see how do we use these subscripts to calculate the molar mass of the compound. And I've already written the molar masses of the individual elements. Now I just rounded nitrogen and oxygen to their whole numbers because they're very close. But cobalt I kept as 58.9. You're welcome to use these, or you can use the ones that are in your periodic table. We should get, roughly the same answer within, 1 or 2% difference. So again, our table or our triangle. So we have the mass, we have molar mass, and we have moles. So in this example, we want to go from moles to mass. We want to find the mass of a substance that has this many moles. And so if we're given moles and we want to find mass, moles times molar mass equals mass. And so the first thing we need to do is calculate the molar mass of cobalt-3 nitrate. And pay attention here, because this is a common mistake that a lot of students make. This 3 here is important because the 3 gets distributed to the nitrogen and to the oxygen. So instead of 3 oxygen, we actually have 9 oxygens, because it's 3 times 3 and 3 times 1. So you have to make sure whatever's in parentheses, we take and we distribute to what's inside the parentheses by multiplication. So since there's a 3 here, 3 times 3 tells us there's 9 oxygen. And so the molar mass of cobalt 3 nitrate, we have 1 cobalt, 58.9. Now that 3 there means we have 3 nitrogens. So 3 times 14 plus 3 times 3 makes it 9, so 9 times 60. So now we add up the individual components and we'll get the molar mass of this compound. We get 244.9 grams per mole. So what this means is that 244.9 grams of CO, or cobalt 3 nitrate, equals 1 mole of cobalt 3 nitrate. So notice here, before we do the actual calculation, that 1 mole weighs 244.9 grams. But up here we have less than 1 mole, so our mass should be less than 244.9, because 1 mole weighs 244.9. If we have less than 1 mole, it's going to weigh less than 244.9. So now we'll set up our train track. We have the moles, 0.00487. And we know that 1 mole is 244.9 grams. So what's on top, we multiply. And we get 1.19 grams. And so this is the mass of cobalt 3 nitrate in 4.87 times 10 to the negative 3 moles. So now we're going to level 2. So that was level 1. How do we interconvert between mass and moles? Moles and mass. We need the molar mass. So molar mass links us between mass and moles. It's kind of like the middleman between the two. You have to go through molar mass to go from mass to moles. Now we're going to add another layer to that. So now we're at moles. Let's say we want to know how many atoms we have in a particular quantity of an element. So say we have 30 grams of carbon, and we want to know how many atoms of carbon that we have. And so the first thing we're going to need to do is we're going to need to convert between mass and moles to get moles. So if we have the mass of something, we need to find the moles of carbon to get the atoms. And so once we have the moles of carbon, then we use, and sorry here, the symbol for moles is typically N. Once we have the moles of carbon, then we multiply by Avogadro's number to find the entities. And since we're dealing in this case with an element's entities would be atoms. So in this kind of flow chart here, if we start with the mass of an element, we have to get to the moles of the element first, and then we can convert it to the number of atoms. So we have to go mass to moles, moles to entities. You have to go, in this case, moles is the middleman between mass and atoms. To go from mass to atoms, you go through moles. And the reason this is, if we draw our triangle that we had on the previous slide, so this is mass, molar mass. And I'm going to use the symbol for N for moles. Now I'm going to draw a second triangle with Avogadro's number. I'm not a great artist, but I'll try my best. So we have Avogadro's number. We have moles. And then the third thing is entities. And again, entities can be typically atoms, molecules, or formula units. And so notice here that the common factor between both of these triangles is moles. So here we have moles when we have mass, and here we have moles when we have entities. So moles is the common link between the two. And that's why in this flow chart, when we want to go from mass to entities, we have to go through moles. So let's say, for example, we have 30 grams of carbon, and we want to know how many atoms of carbon do we have. So in order to do this, our first stop is to find the moles of carbon. And then once we find the moles of carbon, we can go on to find the number of atoms of carbon. Now to find the moles of carbon, you see here molar mass is our ticket. So what we would do is we'd find the molar mass of carbon, and if you look on the periodic table, the molar mass of carbon is 12.01 grams per mole. So now if we set up our train track here, we can go from mass to moles. So we start with 30 grams. So we have 30 grams. Oopsie doopsie. 30 grams of carbon. Now, since we want to go to moles, if we look at our top triangle, to go to moles, it's mass divided by molar mass. So this 12.01 goes on the bottom. And the 1 mole goes on top. And so the moles of carbon is 30 divided by 12. We get 2.5. So this is the midway station. Moles of carbon. So we're at the moles now. We need to go to number of atoms. So here pay close attention, because to go to number of entities or atoms is moles times the Avogadro's number. And you don't have to memorize Avogadro's number. It's always going to be given to you on an exam. You need to know how to utilize Avogadro's number. So we're going to multiply by Avogadro's number, which is 6.022 times 10 to the 23rd atoms per mole. So 1 mole of carbon, as we said earlier, has this many atoms. So when you do this operation, you're going to have to put the number in scientific notation. And if you're using a TI-30, what you would do is you would type in 2.5 times parentheses 6.022, and then you would hit second x negative 1, and you'll see a capital E show up. Then you type in your exponent and close parentheses, and it'll give you the resulting number. So 1.506 times 10 to the 24th carbon atoms. Now let's look at some more examples. So here I just want to show you how it can change with compounds. So I forgot to change a few things, but this should say compound. And you can disregard the bottom here. We're not going to discuss that today. So for compounds, we take the mass of the compound. Again, we convert it to moles of the compound. And then once we have the moles of the compound, depending on whether it's covalent compound or ionic compound, we can determine the number of molecules for a covalent compound or the number of formula units for an ionic compound. And once you know that, then you can actually, just to give you a little prequel of, down the road, you can actually determine the number of a particular atom in the molecule as well. But this is the route we're going to take. Again, same thing with an element, except with compounds, just different terminology. We use molecules for covalent compounds, formula units for ionic compounds. But it's the same process. So here we want to know how many formula units of calcium chloride are in 6.73 times 10 to the negative 2 moles of calcium chloride. So here we have moles, and we want to find formula units. So if we look at our triangle, and I'll use FU for formula unit, so I don't have to write entity. So formula units is on top. Avogadro's number is in this corner. And then we have moles. So in order to find the moles, we need to take the formula units, or excuse me, in order to find formula units, we need to take the moles and multiply it by Avogadro's number. So we set up our train track. So again, moles times Avogadro's number. So we have our moles. Now for Avogadro's number, it goes on top. 6.022 times 10 to the 23rd. And again, I use the abbreviation for formula units, and that's in 1 mole. So now again, we need to multiply. Make sure you use parentheses. So 0.0673 times parentheses. And we get 4.05 times 10 to the 22nd formula units. So this is how many formula units are in 0.0673 moles. And notice, since it's less than 1, our answer is less than 6.022 times 10 to the 23rd.
Oh, how would you write out what you just did? I'm so sorry.
So now we have 2 more examples. We want to know the number of molecules in 182 grams of C4H10. And we want to know what is the mass of 4.57 times 10 to the 25th formula units of calcium phosphate. So we'll look at the first one. And again, I'm going to draw my triangle, so if you want, so you can have a reference. So the first triangle is mass, molar mass, and moles. second triangle is Avogadro's number, moles, and entities on top. So in the first one, we want to find out the number of molecules given a certain mass of a compound. And so again, if we were to map this out, we're going to take the mass, convert it to moles, and then convert it to molecules. So in the first step, we're going to take mass and convert it into moles, but we need, as it shows up in this triangle, we need the molar mass. So we need to calculate the molar mass of C4H10, and then we can convert the mass into moles. So the molar mass is C4H10. So we have 4 carbon. Each carbon is 12. You can use 12.01 if you like. We have 10 hydrogen. Each hydrogen is 1. So that's 58 grams per mole. So 1 mole of C4H10, which is referred to as butane, is 58 grams. So now we have 182 grams C4H10. We're going to divide by the molar mass. To get the number of moles of butane. Again, this is just to get to moles, then we got to go to molecules. So we get 3.138. So now we have the moles of butane. We can find the molecules. So we have moles times Avogadro's number gives us molecules, which is our entity. So we put Avogadro's number on top. And we can determine the moles of, or excuse me, the molecules of this. One 1.89 times 10 to the 24th. So this is the number of molecules of butane in a 182 gram sample. So for covalent compounds, it's molecules. For ionic compounds, as you see in the next example, it's formula units. So now to do the next problem, here again we want to know, or opposite of the first one, we want to know what's the mass of 4.57 times 10 to the 25th formula units. So here we're starting with entities, and we need to get to mass. So to go from entities to mass, we have to go through moles. So what we're going to do is we're going to take the formula units, convert it to moles, and then convert to mass. So we're kind of going, if we think about it, we're going backwards from what we did in the first problem. Now, before we do this, it's best to go ahead and get our molar mass of calcium phosphate. So we have 3 calcium, 40.1. Now remember that this 2 gets distributed to the phosphorus and to the oxygen. So you have to do 2 times 4 to get the total number of oxygen in this compound. So plus 2 in the molar mass of phosphorus is 31, plus 8 times the molar mass of oxygen, 16. I get 310.3 grams per mole. Let me double check. Okay. So the first thing we need to do is to convert formula units into moles. And notice here that it's entities divided by Avogadro's number. So in our train track, Avogadro's number goes on the bottom. We have our formula units, and we're going to put Avogadro's number on the bottom. And that's in 1 mole. So again, always recommended to use parentheses. So what you're going to do is you're going to put parentheses 4.57, second x to the negative 1, type in the exponent 25, close parentheses, divided by 6.022, second x to the negative 1, 23, and we get 75.89 moles. It's always a good check here. If your moles turn out to be something like 10 to the 40th, 10 to the 30th, 10 to the 12th, or some kind of weird astronomical number, it's probably more than likely it's wrong. So your moles should be a relative number, like anywhere from hundreds, maybe thousands of moles to we're talking about 10 to the negative 3, 10 to the negative 4. So if it's outside that window, there's a good chance maybe it's done wrong in the calculator. So, in that region is where your moles should be. So now we have moles. We can calculate the mass by multiplying it by the molar mass. So 1 mole is 310.3 grams. And we get about 23,550 grams. Oh, we got a few more examples. I'll do one more example. That way we can get on to bigger and better things. We won't do that one. Let's see. We'll do this one. So we want to know what is the mass of 3.46 times 10 to the 24th molecules of ammonia. So again, we have molecules, we want mass. So what we're going to do is we're going to take the number of molecules, convert it to moles, convert it to mass. It already gives us the molar mass of our compound. So now we can go ahead and do the first step. Now molecules to moles, we have to remember from our triangle, since we have molecules divided by Avogadro's number gives us moles. And then once we have the moles, we can find the mass by multiplying by the molar mass. So since we're dividing, Avogadro's number goes on the bottom. And mole goes on top. So make sure you use parentheses. And we get 5.75 moles of ammonia. So now we have the moles. And by the way, if you notice that here the exponent on top is bigger than the exponent on the bottom, that means our resulting number should be greater than 1. So it shouldn't be smaller than 1. So if you did this and you got a negative exponent in your moles, that means you've done something wrong. So now we convert the moles to mass, and again, moles times the molar mass gives us mass. So 17 grams, 1 mole. And so this is 97.8 grams of NH3. So that's the mass of 3.46 times 10 to the 24 molecules of ammonia. So again, what we did is we took molecules, converted to moles, converted it to mass. So to go from molecules to moles, we divide by Avogadro's number. To go from moles to mass, we multiply by the molar mass. Now in our next example, we're going to do something just a little bit different at the end because we're looking for a different quantity. So here it says, what is the mass of ethane, C2H6, contains, what is the mass of ethane that contains, I got to work on writing these better, 1.23 times 10 to the 25th carbon atoms. And here in parentheses it says 1 molecule of ethane has 2 carbon atoms. This is just a slightly different twist to what we've been doing, and it gives us Avogadro's number as well. And here, remember, we're dealing with ethane. Ethane is a molecule, so we have molecules per mole. And so the way we're going to approach this problem is we're starting with number of carbon atoms. From the problem, we know that we can go from carbon atoms to molecules. So we're going to go from carbon atoms to molecules of ethane. Once we go from molecules of ethane, we're going to go to moles of ethane, and then mass of ethane. So again, since it told us that there's 2 carbon atoms per a molecule of ethane, well, we can take the number of carbon atoms and convert it to molecules of ethane. And then once we have the molecules of ethane, we can convert it to moles of ethane and then to mass of ethane. So here we do our first train track. .23 times So we have that many carbon atoms, and we know that for one molecule, there are 2 carbon atoms. So you see the carbon atoms cancel out. We get 6.15. So now we have molecules of ethane. So if you look back at your little triangles we wrote on the previous slide, you know that when we have molecules divided by Avogadro's number gives us moles. So we have the molecules, we're going to divide by Avogadro's number. To give us moles of ethane. Again, when you do this, make sure you use parentheses. And we get 10.21 moles. Again, notice that the exponent on top is bigger than the exponent on the bottom, so our answer should be larger than 1, which it is. So now we have the moles of ethane. We can find the mass of ethane by multiplying by the molar mass. Oh, and we need to calculate the molar mass. So the molar mass, we have 2 carbons, 12 grams each, plus 6 hydrogen, 1. We get a molar mass of 30 grams per mole. We get 306.3 grams of ethane. So if we want a sample of ethane that contains 1.23 times 10 to the 25th carbon atoms, it's going to have a mass of 306.3 grams.